Okay, hello everybody. I think this is recording all right here, and we have some responses here about how should we do the video lectures, and it seems that the majority is recommending that we do the asynchronous and post the videos on the day of lecture, and you will watch it. I will try that, and for those of you who wanted it to be synchronous, let's see, maybe one of the things I can do is to try and be present for some of those so that you can either type questions or maybe directly after the video I can clarify some things. I'm not sure exactly what's the best way to do that, so we will learn together. Okay, so here is our plan for today, and we will be taking a look at magnetic fields, forces, and we'll also be taking a look at what happens basically when you put two wires next to each other. And I'll talk a little bit about magnetic materials, and then we'll jump on into chapter 25. I'm going to try to abbreviate a few things and hit the high points in an effort to keep us moving forwards. We have our midterm coming up on the April 15th, and I'd like to ask you all for your input about what we should do about that and what the format of the exam should look like, if there's things that we should change. I'm thinking about doing it as a multiple choice for a good portion of it, and then your free responses will be there will be some numerical answers, and so that will be done on Blackboard, and we'll do it in a similar fashion for the final exam. So, okay. Let's go ahead and start with a little bit of a review here. So some of the things that we learned from last time was that, let's see if I can get this out of the way here. Okay. We learned from last time that if you have a charge and that it's moving in a magnetic field, right? So in other words, this would be a magnetic field that's pointed into the page here. And if we have a charge that's moving, we can use the so-called right-hand rule, where my index finger was pointed in the direction of the velocity vector. The middle finger, so I'm going to say right-hand rule here. The middle finger is going to be pointed in the direction of the magnetic field, and then the thumb will be pointed in the direction of the actual resultant force. So that's our right-hand rule. So if the index finger is pointed to the right here, and the middle finger is pointed into the page, then that means that the actual force in this case will be pointed up. So that's one thing that we learned from last time. Let's see here. Let me just bring up the slides here to take a look at what we learned from last time here, just to remind myself here if there's something else that I'm missing in terms of discussion. Oh yeah, so we also were talking about a loop of wire and how that would work. Right. Okay, so if we had a single wire, and one of the things we did a demonstration of is that we saw that if your thumb points in the direction of the current, then your fingers will go in the direction of the magnetic field. And that also if you had a loop of wire, then for example, if your thumb points in the direction of the current, then your fingers are coming through the loop and showing the direction that the magnetic field is going through this hoop here. And so we had a number of formula. This one was for the magnetic field that's some distance away from a straight wire. And then we also had another equation for the magnetic field at the center of a loop of wire. Okay, so that's our discussion, just some basics. And then we also then started to touch on how does that work then if you have two wires that are near each other. So let's go on to talking about that now. So So if we have two wires here, one has current going up and one has current going down. The first one, we'll call I1, is going to make a magnetic field in the region of the second wire that's pointed into the page or into the screen in this case, right? And so we can basically look at a bunch of positive charges moving downward as that velocity vector being our index finger pointed downward, the middle finger now pointed into the screen, and based on that I can see that the force is going to be pushing out to the side. So here I'm going to just draw that in here, that there's going to be a force pushing this wire out to the side here. If we took a look at I2, well, that's generating, if you use the right hand rule, your thumb points down, that means that it's going to be generating a magnetic field in the region of I1, which is also pointing into the screen. So if I use my right hand rule here for the force on the charges, if you have a bunch of positive charges moving upwards, that's my index finger, and the magnetic field is pointed into the page, that's my middle finger, then the thumb is going to be pointed out to the left. And so in that case, we're going to have a force that points to the right in this, into the left in this case. And according to Newton's third law, these arrows should be equal and opposite each other. So maybe if I want to be really exact here, I can do this, and I can flip this one around here like that, and then I know that they're really equal and opposite each other. Let's take a look at the second situation here and figure out the forces. So again, use your right hand, thumb points up along the direction of the current, and then immediately that tells you that the magnetic field direction in this area here, where the I2 is pointed into the screen. And then again, we do the second right hand rule, which my index finger is pointed up. Here I'm going to briefly go to the camera here. So my index finger is pointed up. My middle, that's the velocity of these that's the velocity of these charges moving upwards. The index finger is going into the screen, and then my thumb is pointed in the direction of the actual force. So index finger up, middle finger into the screen. It looks to me that this is going to generate a force that pulls this guy, and here I'll just make the arrow a little smaller here just so you can see it. It's going to be pulling this I2 in towards I1. Let's take a look at the other scenario where I2 is creating a magnetic field, where if I use my thumb as the first right hand rule, it's generating a magnetic field in this region I1, which is coming out of the screen. So again, use the second right hand rule. Index finger points up, the middle finger is pointed out of the screen, and therefore your thumb is now pointing to the right. So you should be getting that these wires should attract in this case, and the wire should repel in this case. So this is kind of the way to do the right hand rule here. The I is going to be the direction of the charges are moving. The magnetic field is pointed in this direction, and then the force will be in the direction of your thumb. So we can apply that to this situation here and find out that wires that have currents going in the same direction attract, whereas wires that have current going in the opposite direction actually repel from each other. Okay, very good. The force, the magnitude of the force that we would actually want to compute these forces, we're going to use mu naught. That's that permeability constant. And so we actually use that from the last lecture slides here. Let me see if I can copy and paste that again for your convenience here. Where is that here? Let's see, mu naught. There we go, mu naught. Okay, it's that permeability constant. And I'll just put that in here just so you can remember what that is. Then L is the length of the wire. I'm sorry, yes, and the length that where they are actually close to each other. Okay, maybe some of the wire goes way over here and the wire goes way over here or something like that. This wire may go over here, but for this moment they're close to each other. The distance that they are away from each other is d, and then the currents is going to be I1 and I2. That's the current that's going through the top one here and the current that's going through the bottom one. And so whether or not they're attractive or repulsive has to do with whether the currents are going in the same direction or in the opposite direction. Okay, so let's take a look here at a reading check question. Let's imagine that there are 3 wires. Can you compute the magnetic force magnitude and direction on each wire in this figure? Well, I'm going to actually copy this picture down onto my paper, and then we'll take a look at it together. So force is equal to mu naught L times I1, I2 over 2 pi d. And this one is 10 amps going this way. This one is 10 amps going this way. And this one is 10 amps going this way. So they're 50 centimeters here, or in other words 0.5 meters, to put it into SI units, is the total distance across here. And each of them are 2 centimeters apart, in other words 0.02 meters, 0.02 meters. So let's go ahead and make a calculation together. I'm going to go ahead and move to this camera here, and it looks like I have some sunlight issues here, so I'm just going to pause and okay, so here we are. We've got the different currents here. Well, I know that according to our looking at our slides from before here, that if the currents go in the same direction, they're attractive, and if the currents go in the opposite direction, they're repulsive. So in this situation here, I would say that these ones are going, so wires number 1, 2, and 3 is what we'll refer to them as for right now. Wires number 1 and 2 are going the opposite direction. And so if they're going in the opposite direction, then they should be repulsive, right? So in other words, if we're looking at how the force is of number 1 on number 2, we can say that the force of 1 onto 2 is going to be pointed in the downward direction. And the force of number 3 on 2, well, the force of 3 on 2, these are going in the opposite direction currents. And so in this case, opposite direction currents means repulsive. And so that will actually be in the upward direction. Okay, very good. So in other words, we're going to have 2 contributions here, right? I can already tell that that since they're equally distant from each other, and since the currents are actually the same in this case, I can actually tell that those are going to cancel out, and that there should be no net force on wire number 2. I can actually already see that just based on looking at that and saying, well, wait a second. These are all the same currents here, 10 amps, and they're all the same distance away. One is pointed up the force, and one is actually pointed down. So that means that we're going to have no net force on the second wire. Let's take a look at the force on the first wire. So the force on the first wire from the second one, so F2 to 1, we agreed was going to be repulsive. So that's going to be pointing up. And the force from 3 to 1, those are going in the same direction. So those are going to be attractive. So that means it is going to be pulling it down. Just make sure I got that right. It's hard to explain things and do it at the same time. They're going the same direction, so it will be attractive. Okay, that seems right. And so notice that the magnitudes will probably be different though, because the distance from wire 3 to wire 1 will actually be twice the amount of distance. So finally what I will do is work out the force on wire 1, and this will be equal to the force from 2 to 1, and that will be in the plus direction, and then I'll say minus, I'll just put plus there to remind you there, minus the force from 3 to 1. And so putting this all together, I will say that this is equal to mu naught times L times I1, I2 divided by 2 pi times the distance, right? And in this case, from 2 to 1 is 0.02 meters minus mu naught L times 10 divided by 2 pi times 0.04. The L in this case is 0.5, and the mu naught is a constant, which is going to be mu naught will be equal to 1.26 times 10 to the minus 6. And we won't worry about writing down that crazy unit, Teslas, meters per amps, because we know that this is all going to work out, and we're going to be left with a force that really is in newtons. Okay, so finally we can put this all together here. I'm not going to solve this by plugging in all the numbers, but I will say that this term is going to win, right? This is going to be the dominant term here. Because this number here is smaller, and so the overall net force is going to be in the upward direction. So that's how we can figure out the direction of the force, and we can plug in all those numbers, and we can figure out what the overall force is on this wire. So here, actually, maybe I just do it for just this one, and then so in other words. We're going to have mu naught, which is 1.257 times 10 to the minus 6. This is going to be multiplied by 0.5. This is going to be multiplied by 10 times 10, which is 100, divided by 2 times pi times 0.02. And so now I've got that part for the 1, and I'm going to subtract that from this thing, except the only thing that's different here is a 0.04 in this case. So finally, the number is actually, of force is actually equal to 2.5 times 10 to the minus 4 newtons is the force, the total force on wire number 1. You can follow the similar logic to figure out what the force would be for the force on the third wire, but I will leave that one for you to do. Okay, we can also see that we can have a force between current loops, and notice that very similarly, loops that have the current going in the same direction will be attractive to each other in the same way that here the line currents going in the same way we're attracted to each other. And loops that are going the opposite direction will have a repulsive force. We can also see that when we have a loop of current, we can actually see that, so it looks like a complicated diagram, but we just have a loop of current here that's in a magnetic field. This magnetic field here is kind of going to the right, basically, in this 3D picture. And if you looked at it head on, coming from this axis here, you'd actually see that we have part of the wire, the one that's going, the current is coming out of the screen right now. If you use your right-hand rule, you can see that your index finger is pointed out of the screen. Your middle finger, the B, is pointed to the right, and then your thumb is pointed up. And if you do the same thing down here at the bottom, you'll find that the bottom part of this loop here, which is this one here, has a force that's pushing down. And so in this sense, there's a tendency for the magnetic field to cause the loop to start spinning. If you work it out for this side and this side, you'll actually find that there is no net force on either of these two sides, just on the top and the bottom parts of the loop. So now what's useful about this? Well, it can be used to make an electric motor. And so if you put a little loop of wire in a magnetic field and you have some current going through it, it can actually make this electrical energy turn into energy of motion, which is mechanical energy. So that's an interesting connection to our previous discussion around mechanical energy that we did in Physics 125. So if you wanted to calculate the torque on a dipole moment, on a dipole that's in a magnetic field, you can take the current times the area, right? So in this case, for area, this would be like pi r squared, for example, if it's just a circle, times the magnetic field, times the sine of the angle between the magnetic field and where the magnet's pointing. So in other words, if the magnet's pointing along the magnetic field, then you have an angle of 0. But if the angle is pointed all the way at 90 degrees with respect to the magnetic field, then you basically have your maximal amount of torque. So now the question might be, if you wanted to go a little deeper, is like, what is the reason why things are magnetic, right? Well, it's actually the electrons themselves that are actually behaving as a little tiny magnets. And we'll just kind of touch on this, that maybe you've heard of NMR or nuclear magnetic resonance, or MRIs, magnetic resonance imaging. And the way that it works actually is that we pulse little magnetic fields, and you actually, all of the water molecules in your body actually respond to those magnetic fields, and they produce, they jiggle a little bit. And then, so it turns out we can actually see the response of that jiggling, and you can allow it to see what's happening inside of the brain. Okay, so just in the effort to kind of shorten things here, I'll just mention just very briefly that there are some materials which are ferromagnetic, which means that they're always magnetic. And then there are also other kinds of materials that are only sometimes magnetic. And I think I'm going to move through these ones here, and I'm not going to spend a whole bunch of time talking about it, but I just wanted to mention that there are other materials which are called a paramagnet or a diamagnet. And these ones behave a little bit differently here. The paramagnet will only create some magnetism when it's in a magnetic field, and a diamagnet will create something that's actually in opposite to the magnetic field. So I'm just going to kind of go over that one. I'm going to go past that one. There won't be a ton that you're responsible for on the magnetic materials for our exams, but I just wanted to give you an idea that's kind of the origin of magnetism. Okay, so moving along from there, so let's talk about magnetic induction now. So basically, I think so. Maybe you had the experience of walking by there's some glass cabinets on the second floor of the physics building, and I realized it's not really possible to go there right now, but maybe you had the experience of pushing this button and you actually saw that there was a little hoop of metal that actually jumped, and this is a result of electromagnetic induction. I am going to just pull up a simulation here. And I want to demonstrate something here with you, is that if I have a magnet, and if I just bring it nearby a loop here, try to do it slowly so you don't see anything, but I spoiled it. If I just bring it very slowly, nothing really happens. But if I suddenly move it, or suddenly move it inward into this coil, you actually notice that for the moment while it's moving, then we actually get some current that goes through. And so we can, in other words, we can generate current just based on moving magnets past a wire. So that's really interesting. That means that you can turn mechanical energy into electrical energy. So this is called Faraday's law, and this is the topic of electromagnetic induction that we'll be covering. And so we'll just cover the first part of this today, and then we'll move on right after the break to go a little bit deeper into this. Okay, so please take a moment to see which of the following will actually cause an induced current in a coil of wire. Well, based on our recent experience that we saw with the simulation, we can see that a magnet that's being moved into or out of a coil will actually give you some induced current. This is a bit bizarre, I have to admit. It's not something that I would have ever expected, that just simply by moving a magnet that we could actually get some current. But this is in fact the physics that's going on behind a generator, is that if we can get something to move, then we can actually begin to make some electricity from that motion. Okay. So there was a physicist back in the 1800s named Michael Faraday. Maybe if some of you watched the TV series Lost, you saw Daniel Faraday, who was doing different electromagnetic experiments, but it was loosely based on this character, Michael Faraday. And one thing that he noticed was that when he had an iron ring and he wrapped it up a few times with some wire and had a battery connected, and if he were to suddenly, remember when I did that thing where I connected the battery and then suddenly there was a whole bunch of current? So he did something like that, except he wrapped part of it around this iron core. When he wrapped another side of it around a current meter, he actually noticed that the needle jumped the moment that he connected this switch. But if he left it connected and there was a lot of current going on this side, there was not actually a lot of current on the other side. So a steady state magnetic field didn't create a current. So he knew that, and one of the things that we've talked about before is that if you wrapped a wire around this piece of iron, you know that it's going to create some magnetic field in there. And so that magnetic field, turns out it'll go all the way around the ring. So, but it turns out that just having a magnetic field because of this current going through the wire wasn't enough to create any current in there. But it was at the moment where he either closed the switch or opened the switch that suddenly he got a big jump of current. He also did something like this. He said, okay, well, I've got this loop of wire and another loop of wire over here. And the moment that I close or I open the switch, this needle deflects. But if I leave it open or leave it closed, nothing really happens. This thing remains unaffected. So it has to do with changes somehow. And similar, if you were to drop a magnet through this loop, then suddenly the needle deflects, which means that there's current going through. Okay, so let's take a look here at an example. There's a potential difference that's developed across a long wire in a figure, in this figure, as it moves through a magnetic field at 5 meters per second. The magnetic field is perpendicular to the long axis of the wire. So what is the direction and the magnitude of this field? So in this case, we're thinking about, we have some changes in the magnetic field that's associated with this wire that's moving through the magnetic field. And we can consider the effect that that change in magnetic field will actually have to make a difference in voltage across the wire. So do you remember that second right-hand rule, that if we had a charge that was moving through a magnetic field, that charge would experience a force upwards, right? Well, it's true. And so there would be an electric field that would build up across this wire as we're moving these charges through the magnetic field. And so basically, we're producing an electric field inside of a metal, which basically means that more charges should flow. So in other words, it's piling up charges on the bottom as negative and charges in the top as positive. And so there's going to be a voltage difference between the top and the bottom of the wire that's equal to the speed that you're pulling this wire times the length of the wire and times the magnetic field strength. So in other words, we can put those together in this example here, and I'll just work it out here, that we have a voltage difference equals to 0.05 volts. The length of the wire is equal to 10 centimeters, or in other words, 0.1 meters. And the velocity is equal to 5 meters per second. And in this case, we're supposed to figure out, well, what is the strength of the magnetic field in this case? Well, if delta V, the voltage difference across this wire, is equal to V, not to be confused with voltage here, so that's another sort of pitfall that we have to watch out for. So this is V, lowercase v, and this is V, uppercase V, right? So I can try to maybe distinguish those here, is VLB. We notice that we can actually solve for the magnetic field here as delta V divided by V times L. So this is going to be 0.05 volts divided by 5 meters per second times 0.1 meters. And if we put all these together here, now I realize that again we're in this weird world where the units don't really seem to work out to be something very obvious. It's volts per, what is that, meters squared and then times seconds. Well, it turns out that that unit is called Tesla. And so, yep, just like Tesla, like the big company, right? And so if we do 0.05 divided by, and I'm going to use my parentheses here, 5 times 0.1, we're going to get 0.1, and the units is Teslas. And so that is the way that we can calculate the magnetic field strength that's associated with creating that kind of voltage difference. Now, is 0.05 volts a lot? Well, I mean, it's not very much compared with like a usual battery, but it's certainly a measurable quantity. Okay. So let's take a look at another example here. This figure shows a 15 centimeter long metal rod, and it's moving along two frictionless conducting rails at some speed. And the rails have negligible resistance, but the rod has a resistance right here of 0.65 ohms. So we want to know what is the current in the induced rod, and in which direction will the current flow be. Take a moment to see if you can figure out some of those details. Okay, so taking a look at this here, maybe I can remind us of two concepts that we've looked at so far here. One of them is that we saw that this equation, voltage difference, is going to be velocity times the length of that wire times the magnetic field. But the other concept that we've seen so far is that if you had a charge that was moving in a magnetic field, that we can use the the second right-hand rule to figure out what the force would be. So in other words, if I had then a charge that was moving in this direction, we can do index finger is the velocity, middle finger is the magnetic field, and we can see that there's a force that pushes downwards. So therefore, if we had a bar that was moving in a magnetic field like this, I would see that the positive charge would build up on this side, and the negative charge would build up on the other. So if that's true, then what we can actually say then here is that our bar that we have that's moving through the magnetic field, which is pointed into the page in this case, is going to have a buildup of positive charges on the bottom and negative charges on the top. And that's basically going to be, and so this is connected through some kind of some wire like this, right? And so in a sense, that's like having a battery that's connected to a wire. Now granted, there's also some internal resistance in here, right? So there's some R, which was, I think that we said it was 0.65, is that correct? 0.65, that's right. So R is equal to 0.65, but there's going to be a voltage that's induced here, which is going to be this VLB. So we can figure out now, well, I know that the current is going to be going in the clockwise direction. We'll write clockwise as equal, yeah, we'll write this here. Clockwise is going to be CW, and counterclockwise we'll write as CCW. So counter, sorry, I was trying to go too fast. counterclockwise, we'll write a CCW. So this is going to be a clockwise current here, and the voltage, delta V, is going to be equal to the speed, which was 0.35 meters per second, times the length. Well, what was that length here? That was, oh, I'm sorry, it was 3.5 meters per second. 3.5 meters per second. The length is 15 centimeters. So that's equal to 0.15 meters. And then times the magnetic field strength. What is that magnetic field strength? That is 1.4 Tesla in this case. So we'll have 1.4 Tesla. Sorry, I need to move it up a little bit here. 1.4 Tesla. And if we put all those numbers together here, we'll get 3.5 multiplied by 0.15 times 1.4. And we plug all those together, then we'll see that this is equal to 0.735 volts. Well, that's good, but that's not quite what the question asked, right? The question asked, what is the induced current in the rod? Well, now we have to combine our concepts with what we know from circuits before. So if we have a voltage and we have a resistance, well, we can figure out the current. And I know that the equation that I use is delta V is equal to current multiplied by resistance. So in other words, I is equal to delta V divided by R. So here we have a delta V is 0.735 volts, and we have a resistance which is given in the problem to be 0.65 ohms. So putting all these together here, I can compute this, and I can say that's 0.735 divided by 0.65, and I end up getting, down here, 1.13 amps that's going through this, this circuit. Now, a comment just about the direction here. So I figured out that it was going to be, the direction was going to be going in the clockwise direction. But also, there's another sort of rule, and this is something we'll get into later, which is that a general principle is that nature hates changes. Sounds kind of weird, right? But specifically changes in what? It hates changes in flux. And so, so the flux is actually, in this case, meaning the amount of the magnetic field which is pointed into this loop here. And so we'll get to this in the next discussion. But basically, one way that I showed you a way to figure out the direction of this current, but also you could say that the magnetic field is pointed into the page, but since the loop area is getting smaller, that means that the change is actually coming out of the page, and so then the loop, you should actually have the loop going around in the clockwise direction to counteract that change in how much field lines are actually going through that loop. So if that didn't quite make sense to you, you can use the first way. It's not a problem, and that is that's enough for figuring out the direction of current flow in this configuration. Okay, very good. And so then there's kind of a little bit of like a bonus question in here, which is what force is actually required to keep the rod moving at a constant speed? Well, this is not at all obvious, but if you think about it, the pushing this rod forward is going to mean that there's now a current that's going through the rod. Well, we talked about that if you had a rod, or if you had a wire, and it has a current going through it, and it's in a magnetic field, then there's going to be a force is equal to ILB, right? So in other words, if there is a current that's going through this thing, so the current going down here, a current like this, and remember that the force is equal to ILB, right? And we can use this right-hand rule so that the I is my index finger, the magnetic field is pointed into the page. We're actually going to see that there's going to be a force now generated that's trying to keep it from going this way. So I would actually need to put a force with my hand. So I could call this the force of the hand. And this is the force of the magnetic field. And I would have to counteract that. And so I'm just going to fast forward here to a place in your book here. This is on page 883 of the text. And here you can actually see, this is the force of the magnetic field. This is the force of pulling in this case, but actually it's the opposite way in our situation, is that we would actually be pushing in this case. I don't know, there's not like a, it's unfortunate that it's exactly the opposite case, but I think you can adapt to that. This is the current going up, but if the current's going down, well, then this is going to be the opposite direction here, right? So you can say that the force needs to be equal to ILB, but I, as we just found, was equal to VLB over R. Putting all those things together, you can see that this is VL squared B squared over R. Whoa, that's a lot of things, right? But we can actually put those things together, and so we can say that the force that we would need to be pushing in this case is going to be equal to V L squared B squared over the resistance R. And so again, that's 3.5 meters per second. That's the length of this wire of 0.15 meters squared. It's a magnetic field strength of 1.4 teslas squared, and the magnetic, why did I say magnetic? The resistance is 0.65 ohms. Notice how I'm moving away from putting in the units in these calculations because of the fact that, well, when we add up all the units together, they don't even really make sense, right? We're trusting that if we keep in SI units, that this force is going to be really in newtons. Like, take a look at what the units might actually look like. Meters per second, that's for this part. The length is going to be meters, and then it's squared. The magnetic field is going to be Tesla, and that's squared. And then the resistance is in ohms. I give up. I have no idea, right? Doesn't make any sense. Meters cubed, Tesla squared divided by seconds times ohms? Buh, I don't know. So in other words, what I'm trying to tell you is that when we use all SI units, this is really going to be newtons. So it's greatly simplifying our situation here. I can plug in all those numbers here for you just so in case you wanted to check yourself doing this calculation. So 3.5 times 0.15 squared times 1.4 squared divided by 0.65, and we get equals to 0.237 newtons. So we would have to push this thing with this much newtons here, and that's coming from equation 25.5 in your textbook. All right, very good. So that's all that I have for today, and I think I'm going to try to upload this video here and then stick around for questions as they come up as you watch the video. All right. Have a good spring break, and I will look forward to seeing you when we get back.